All right, so moving on in chapter 2, all about the momentum principle, we're going to look at large forces and short times. So, as you will see, the momentum principle is a powerful tool for modeling all types of situations. And it's something that we'll use all throughout both Physics 1 and 2. So, and in terms of whether it's used today, the momentum principle is one of the primary methods that particle accelerators make measurements and find new particles. All right, so before we get ahead of ourselves and look for theoretical particles, let's just practice some basic models of situations with sudden impact. So, I want to do sudden impact, which is a large force and a small delta t. Okay, so we're going to look at two students running across campus. And they're both late, they're going opposite directions, they're not paying attention, and they run into each other. So they started out with some V initial and some V initial, non-zero, and then they end with some V final 0. So we had a huge momentum change. We went from something to 0 very quickly. And so we want to think about how we can make some reasonable estimates to go after the momentum change in this system. And for this, we need to think is what is the force one student exerts on the other? Okay, and in this we're going to practice making reasonable estimations, because reasonable estimations can get you pretty far in life. Okay, first of all, we need to do a diagram that's going to depict all the forces. So let's model the student right here. And so at the initial interaction, we're going to use the point particle model. So all of his mass is concentrated into a point. We would have the force from the sidewalk pushing up, the force of gravity pulling him down, and then he has velocity in the negative x direction. And then during collision, he would continue to have the force of the earth pulling him down, the force from the sidewalk pushing him up, and he would have the force from the other student. Okay, so, and this is what we're interested in. We're really interested in what is this force. What is the force from the other student? Okay, so to analyze this, we want to start setting this up. And this method of setting up problems is going to be important for the entire class. So we want to list out what we know, list out what we want to find, and it starts by specifically listing what is our system and what is in our surroundings. So in this case, our system is the student on the right. So this is what is going to be forced on, and our surroundings are what's going to bring the force. So the other student, earth, sidewalk, air, etc. Now, note, when you're thinking about the surroundings, you want to think about what's measurable. There's a lot more in the surroundings than what we've listed here. So for example, technically speaking, the force of gravity from Jupiter is acting on these students. It's just that you really can't measure this, and it's not going to make any different impact into what's going on. And in fact, often we will neglect things like air resistance. And the question as to whether or not you can neglect something is it going to make a measurable difference? Are your instruments precise enough that this is important? So in this case, since we're making estimations to begin with, the impact of error resistance is going to be within the realm of error. So it's perfectly reasonable to neglect it. Okay, so if we're going to analyze something, you want to pick an initial and final time. And you want to choose this time segment so you can get the most information. So for example, you don't want to choose the time when the students are really far apart. You want to choose just before impact, because our question lies within the impact itself. And then our final time is when they come to a stop. We don't need to look at when they're laughing in the calf together with each other later. This is the bunch of time that encapsulate what specifically we're looking for. Okay, so now, since this is just a practice in estimation, we're going to do some simplifying assumptions. So students have the same mass. And same initial speed. This is pretty reasonable. The average male college student has a pretty similar weight range. Obviously, if we were looking at football linemen, that we'd be looking at something different. As I said before, we should really just neglect things like friction and air resistance. They're there, but the impact or the contribution they're going to make is really within the realm of error because we are making estimations. Furthermore, we're looking at a tiny delta t. So you always have to ask negligible and over what time period. Okay, so the change of momentum is only in x. Let's look at why this is true. So going back to our force diagram, we have the force from the sidewalk. So right now, if you are standing on the ground, you can feel the force from whatever ground you're standing on pushing up on you, and you can feel the force of the earth pulling you down. These are equal and opposite. So the sum of forces in y is equal to 0. We are only left with the force in positive x of the other student. Thus, if the sum of the forces in y is 0, that would then imply that the change of momentum in y is also equal to 0. So we only need to deal with x. Now, if you wanted to at this point, you could simply state that and then move into working in scalars. I'm going to stay in vectors just to kind of give you a little bit more practice at just getting comfortable with vectors. So let's use the momentum principle. The change in momentum is equal to the net force times delta t. Now, we don't really have anything for this right now, so let's start by calculating the change in momentum. We know that momentum final is equal to 0.000 kilogram meters per second, and momentum initial is equal to whatever we end up using as our mass times the velocity initial, 0.0 kilogram meters per second. Okay, so delta P is equal to P final minus P initial. So delta P is equal to 0.000 minus VI times M, 0.0. And this is equal to F net delta T. Okay, so at this point we've plugged in what we know and we still have two unknowns, so we need to go after some reasonable numbers. Let's see, let's say the mass is approximately 68 kilograms for both students, and the initial velocity or initial speed is 6 meters per second. Could we do an estimate for t? Let's kind of hold off to the side that maybe we could estimate 1 second, and let's see if that's reasonable. To go after what's reasonable, we want to think about maybe a different way. We could go after time. So, because collisions are short, but exactly how short are they? So, when a force is applied to the human body, it compresses. And so we can use this to go after delta T. So let's say these two students hit stomach to stomach, which is ouchy, but not devastating. So students hit stomach to stomach. And they compress, or the student's body compresses 5 centimeters. Okay, so we know that the final velocity is equal to 0 meters per second because we were given it. So we can use this along with the initial velocity to go after average velocity. Because if we have average velocity, we can use the position update formula. So we'll use the arithmetic average. So we know the velocity at the beginning, we know the velocity at the end. We'll divide it by 2 known speeds. And so the average speed is going to be 3 meters per second. So looking at our update formulation for x, because this is only happening in x, we have v average in x times delta t. If you multiply those two things together, you'll get delta x. So we know delta x, it's 5 centimeters. So this is approximately equal to 3 meters per second times our unknown delta t. We solve for delta t and we see that it's approximately 0.017 seconds. So the whole interaction is only about 0.02 seconds. Very short. And this is why it's hard to go after delta t. That is not really a comprehensible length of time. So, how large is the force from the other student? Okay, so starting from, or ending at rest, minus, remember it was going in the negative direction. So we're going to get a positive force, which is just like we predicted with our initial setup. So we have F net, or this is all equal to F net delta T. So we have 0 kilogram meters per second minus 68 kilograms times minus 6 meters per second, 0 is equal to F net times 0.17 seconds. So we'll divide this side by 0.17 seconds and we get that F net is approximately 24,000 newtons, which is pretty big. It's a really large force. Just for comparison, the weight of one of these students would be about 680 newtons. So this is substantially more force than just the force of their own weight. That's why it would hurt so bad. But it could be worse. So let's say those students were to hit head to head. So in that case, you might get compression of about 1 centimeter. And this would actually result in 5 times the force. And on your own, prove. Okay, so what we can see from this example is it's easy, or relatively easy, to estimate speeds and masses of people. Time can be hard to estimate. And this is because we live our lives in seconds, minutes, hours, days, and years. And sudden impact collisions take place in fractions of seconds, which is not really something that we, in the time span that we live in, have a good feel for. So for example, if we would have had the 1 second guess, what that would imply then is, so if we look again at our arithmetic average for velocity, we had our 3 meters per second. And over the course of that interaction, it would mean that student 1 would run 3 meters, thus going directly through student 2, which works out mathematically, but we know it is not physically possible, or at least looking at entropy, so improbable that you would need the universe to exist several times over before something like that would happen. So, thus, 1 second is insufficient. So we arrived to this answer by looking at estimations. And how useful are they? Well, they're really useful. These estimations can get you on the right order of magnitude of an answer. This comes in handy if you're going to have to take a standardized exam like an MCAT, but also for different professions that you can go into, just being able to do a quick and dirty estimation to get onto the right order of magnitude that your answer is going to be is super useful. Also, in this particular setup, so if we go back to our force diagram of the 2 students, we were able to predict that the force would be in the positive direction. So these are all just useful tools to check yourself when you're setting up different types of problems. So what this situation was is an example of an idealized model. And so these are basically any model of a physical situation that is a bit perfect. And the question you also want to ask yourself is, what is good enough? And what you mean by that is, how easy can you set up a system where any discrepancies are not really measurable or within the margin of error? So idealized models are very useful for not only understanding basic physics concepts, but also analyzing real world situations. So as we're introducing different topics throughout the introductory sequence, we will start with idealized models and then allow them to get more and more complicated as we progress.